Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 6, The Chemical Atom. This episode is written in the form of a fictional autobiographical reflection by the French chemist Michel Eugene Chevreul on the occasion of his 100th birthday. While the persons and events related in the reflection are real and accurate, the words I am putting into his mouth are literary license, and they were never spoken or written by the man whose name is one of the 72 inscribed on the Eiffel Tower. I felt that the scope of his life and experience would provide an excellent framework in which to view the tremendous advances made between Lavoisier's death and the chemical congresses of the 1860s and 70s. I hope you'll excuse this foray into historical fiction as a means to understand how the narrative moves forward. The year is 1886, and on the occasion of his 100th birthday, the venerable French chemist reflects. How much has changed in the course of my life? When I was born, there was the ancien regime and a king, though not for very long. In my time, I have seen many so-called revolutions, always passing from one thing to the next. I have lived through the Committee on Public Safety and the mad tyrant Robespierre, the armies of Napoleon with their triumphs and disasters, and the restoration of the monarchy first destroyed and then replaced. I rode out the tumultuous revolutions of 1848 that swept the capitals of Europe and brought the second Napoleon emperor, who called himself the third. With my countrymen, I suffered through our most recent humiliation at the hands of Bismarck and Wilhelm, though France has rebounded well from the defeat, and will, in the right time, recover what was taken. But such political affairs have always been secondary to me. While certainly they impinged on our lives from time to time and disrupted the important work of understanding nature, my interests have been primarily focused on those investigations, both practical and theoretical, of the nature of matter. I have been a chemist throughout my life, studying topics as varied as color and the nature of those fats and oils found throughout the natural world, in both plants and animals. I've also been an unrelenting opponent of the charlatanism that pervades our modern world, including that so-called psychical research, spiritualism, and the magical pendulums of dowsing and table-turning. All of this, however, has been lesser work when considered in the light of the great changes that have occurred in my field of study. This is the revolution that will be lasting, I think, one that will never be undone. I was born at a time when it was important to know one's lineage, but I now live in a time when perhaps that is less important, at least in some places. My lineage is of a line of physicians and surgeons, and it was in their footsteps that I was going to walk, but something funny happened along the way. In my studies, I was a bit more talented in the laboratory than my fellows, and I caught the attention of a prestigious man, a chemist, who had a lineage of his own. My mentor was the great Louis Nicolas Vauquelin, the discoverer of beryllium and chromium, and it was his assistant I became in 1803, after I moved to Paris, and it was his chair I assumed on his passing in 1829. His line in chemistry goes back to even more great investigators, Fourcroy, Bertha Let, both of whom had worked with the incomparable Lavoisier in establishing the very language we now use to describe the compounds we react and study even to this day. Many were the issues these two studied. It was Bertha Let, while on one of Napoleon's expeditions to Egypt, who had noticed that in the lakes there, that chemical reactions could be reversed, depending on the amount of various reactants, and that when the possibility of both the forward and reverse reactions were available in the same place, there was always an equilibrium that could be reached. He did not understand why this would be the case at the time, but his researches and results were numerous. One thing he said he observed was that there were no fixed ratios for reactions to take place. In his eyes, there were times when making table salt required 1 part sodium and 1 part chlorine, but at other times, 2 parts chlorine might be required. This result brought some controversy, it could be said. It was Proust in Spain who disagreed. Proust had said that in his researches, substances always combined in fixed ratios by weight. Making salt always required 1 part sodium and 1 part chlorine, and there was no other combination. Thus was the debate cast, and it was a controversy carried out as all scientific disagreement should be. Both men held to their positions, but with deference and courtesy in the communications with which they presented their findings. It was Proust who was in the right, of course, and his law of definite proportions was a big step in the way forward, even if many people didn't see why at the time. It wasn't until the weaver's son in Britain came along that the answer became clear. Dalton had reached back into the mists of time through the words of Boyle and Newton to see the truth, that the atoms of Democritus and Epicurus had to be real, at least in part. His insight was based on the work before him, but he was the one who saw how all the evidence pointed. First, there was Lavoisier and his conservation of mass. While this did not require atoms to exist, they explained why nothing was gained or lost. Then there were the reversible reactions of Bertha Let that could be understood through atoms combining and recombining. But the 2 key pieces came from Proust and the work of Richter. Richter had shown that all chemical processes were based on mathematical laws, just as Kepler and Newton had done for astronomy and physics. His stoichiometry had set us all on the path of determining the mass ratios of various chemicals and reactions. Along with Proust, he had shown the constant combinations of compounds, but he had published tables of the weights in various reactions. What Dalton saw in those weights was a key. You see, there are some elements that combine with other elements in more than one way. Take carbon and oxygen, for instance. Reacted one way, 1 mass of carbon will react with the exact same mass of Lavoisier's oxygen to form a gas. However, if reacted another way, 1 mass of carbon will react with 2 masses of oxygen to form a different gas. Dalton did the same thing with nitrogen and oxygen and found the same result. He did this with many sets of elements and found that in each case, if multiple compounds could be formed, the masses of the elements always combined in even multiples of the other compounds. Dalton called this the law of multiple proportions, and with the other evidence, he made the intuitive leap of explanation. He explained this by saying that all matter was made of atoms, like Epicurus of old. His atoms were the same as the Greeks in some ways, but different in others. First, he said that they were hard spheres, that they were indivisible in the course of chemical reactions. Second, he said that while each element was a different sort of atom, all of the atoms for a given element were the same. Most importantly, he said that all of the atoms in a given element had a constant unique weight that was different than the atoms of other elements. He said that the chemical reactions were combinations of atoms from one element with the atoms of another. Once someone asked him how he had gotten to that point. How had he seen the big picture? Dalton said that he had been considering the atmosphere, which was of particular interest to him. He knew that it was a mixture of gases, oxygen, nitrogen, carbon dioxide, and water vapor among them that made up the atmosphere. What he didn't understand was how they stayed mixed up like they did. Why didn't they separate like water and oil, with the less dense gases rising to the top and the more dense gases sinking to the bottom? He realized that the only way the atmosphere could be mixed was if the gases could travel through each other. However, this meant that there had to be spaces between the constituent things that made up the gases. and it was then that he recalled the void of the Greek and Indian philosophers. With that void came atoms, and he realized that for the atmosphere to be mixed, the gases had to be made of atoms moving through a void. Upon realizing this, he said he recognized that if these atoms could stick together, they could form chemical compounds. He also saw that in chemical reactions, these compounds could be rearranged, and so he realized that he had hit upon the solution to many problems that were plaguing chemistry. He was right, of course, though many of us here in France failed to see it at first. Who was this poor Englishman who brought back the discarded ideas of the ancients anyway? Many knew that he was only a mediocre technician in the laboratory, and that his experimental evidence was sloppy, but he had an explanation that tied together many things, and that was hard to dismiss or set aside. What was soon seen was that there was a need for better weights of compounds. For too long, we chemists had neglected making careful measurements of all of the things that we had worked with. We couldn't refute Dalton's picture, nor could we confirm it, as we didn't have enough good data, at least until Berzelius. Oh, what a work he did. What a master the Swede was. Over 2,000 compounds he measured with such precision and care. Nothing so remarkable has been done in the laboratory before or since. It was Berzelius who first applied electricity in chemical research, though it would be Davy and Faraday who would use that tool most effectively. He supported the atomic theory of Dalton by explaining that atoms might combine with each other because of that electrical affinity. It was also Berzelius who did away with all of the arcane alchemical symbols that had been used for so long. So simple was the shorthand that he replaced it with that many of our fellows were thrown into fits of rage that this upstart would discard centuries of tradition. But such was the time. Chemistry was changing and leaving behind the ignorance of the ages. Just as Lavoisier changed how we spoke chemistry, Berzelius would change how we wrote it. Today it is hard to find a young chemist who does not use the Swede's simple system of letters and subscripts to describe the reactions they are working with instead of the arcane symbols and pictures, hieroglyphs really, that I first learned in my youth. All of this, however, was a precursor to that work that I briefly mentioned. It was Berzelius who over many years found the relative weights of each type of atom. Like Dalton, he started with hydrogen having a relative weight of 1, and by weighing different compounds and comparing their constituent atomic parts, he was able to tease out the weights of the elements. Day and night he worked, and on at least one occasion, he was nearly killed with the reaction becoming too violent. At the end of his work, he had weights of some 50 or so elements, a few of which he had discovered himself, which were unassailable. It was such a monumental work that it boggles the mind, even now, to think of it. You would think that such a wonderful piece of work would make things better, but instead, that wasn't the case. Instead, the weights of Berzelius helped contribute to the most difficult confusion. The precision of his measurements had clearly established Richter and Proust's law of definite proportions, that in turn lent support to Dalton's theory. However, there was a problem with the gas laws we knew governed the very things Dalton had claimed led him to the atoms in the first place. It was my colleague, Joseph Louis Gay-Lussac, who had run across the difficulty. Like my mentor, he too studied under Bertha Let and Fourcroy, and he continued working in the area of chemical and analytic chemistry, specifically in pneumatic chemistry. His work with gases called Dalton's atomic theory into question. He had experimented with many gases, and he had found that the volumes of gases always combined in simple ratios with each other. For example, 2 volumes of hydrogen gas combined with 1 volume of oxygen gas to make 2 volumes of water vapor. This, of course, seemed to be evidence for Dalton's theory. However, why did the resultant volume come out the way that it did? The biggest question came from combining 1 volume of nitrogen gas with 1 volume of oxygen gas. The result was 2 volumes of nitric oxide gas, not the one that Dalton would have predicted. It was quite a puzzle indeed. Dalton said my colleague had to be wrong, while Gay-Lussac questioned Dalton's theory. The controversy threw all of chemistry into confusion, and for quite some time. If we'd only known about the Italian professor and his insight into the problem. There was so much going on in the world of chemistry at the time. It seemed that every year someone was discovering a new element, whether it was Davy at the Royal Institution or Brasilius or one of his students in Uppsala. The language didn't help either. While Lavoisier and Brasilius had cleaned up a lot of the old confusion, all of this work introduced new terms that were just confusing. They just weren't used precisely enough. Dalton insisted on using the words atom and molecule interchangeably. Some used atom, while others insisted on corpuscle. It didn't stop us from doing more work, but it did keep us from always understanding what we were doing sometimes. It was during this time that Wöhler started his work in what would become organic chemistry, and I did my investigations on the fats that are not only found in animals but in plants as well, the same fats in different things. Sometimes Dalton's theory helped, and sometimes it didn't, but we pushed forward anyway. It was during this time there was a student I had, an Italian, and something of a revolutionary was he. His name was Stanislao Cannizzaro, and he's a senator now in a unified Italy, if I remember correctly. He told me that he knew of a solution to the problem with the gas reactions. He had learned it from a professor he had had when he was younger. Amedeo Avogadro was the professor's name. Who had ever heard of him, teaching in Turin? It turned out that we all had the picture of gases wrong. We thought that gases were constituted from single atoms of elements that made up the gases. Certainly, we knew that carbon dioxide was a combination of atoms, but oxygen, and indeed all pure elements, were thought to be just single particles, single atoms. Most of us assumed, like Dalton and Brasilius had, that atoms of the same type would electrically repel each other. But Avogadro said that in gases, many of the elements would have their atoms combine in pairs or perhaps even larger groupings. When these multiple atom molecules reacted with other molecules in gas reactions, there was more than one atom to do the reacting. And this solved the volume problem perfectly. It removed the final barrier to accepting the atomic theory of Dalton. Of course, we didn't see Avogadro's papers back in 1811 when he published it, nor a similar work by Ampere 3 years later. The idea languished in the intellectual backwaters until 1860. That was when the problems had reached such a state that we chemists agreed to gather to see if we could come to some conclusions about these and other issues. All of the great chemists of Europe were there, and it was in this forum that Cannizzaro put forward the ideas of Avogadro. At the end of the conference, he gave out a pamphlet that outlined the ideas, and it was through this that slowly others began to see the truth of Avogadro's idea. It was a great work, not just by Avogadro, but by Cannizzaro as well, who made the ideas of the professor from Turin clearer and more generally applicable. And so this is where we find ourselves in this day. There is still so much work to be done. Meyer and Mendeleev have organized the elements now, and their structure guides our search for more elements. In Mendeleev's table, there is clearly structure that hints at deeper knowledge to be discovered. The nomenclature and symbolic representations of Lavoisier and Brasilius are spreading throughout the chemical world, and students learn these now. While there are still those who question the reality of the atomic model of Dalton, the physicists have shown through their kinetic theories that atoms must exist. Wöhler has debunked the vital force hypothesis, and we're beginning to understand the chemistry of life, even now producing dyes that were once only available through natural sources. So good have we become at this that Perkin in England created a color, mauve, that was unknown to the world prior to its synthesis. He was studying quinine when he reached the discovery. Not all of our work has been for the benefit of humanity, however. It was Nobel who created dynamite, which was supposed to help work the earth in construction projects, but is now sold to governments in huge quantities for the purpose of making war. He's made a fortune with it and his other munitions apparatus. But one wonders what the judgment of time will be of all that wealth acquired through the suffering of so many. Nevertheless, we stand on the precipice of an amazing time. The world improves each day, and progress carries all of humanity forward. Each year brings improvement to man's lot, and surely we will put behind us all of the barbarity that has plagued our species for the millennia. It is a new time, and chemistry will lead the way, I think. There are still mysteries to be understood and problems to be solved, but given how far we've come in the last century, it is hard to imagine that we aren't nearly done with the work. For my part, I will continue to work to educate the next generation of thinkers through my writing and my teaching. It is they who will take us to a place where the savagery of the past will be left behind and a better world will be founded on the power and promise of reason triumphing over charlatanism and superstition. In the next few episodes, we'll look at the progress made in Chevreul's lifetime in understanding and supporting this new atomic theory that Dalton had come up with. We'll look at evidence both in the fields of chemistry and in the fields of physics. For more information about the science that's being talked about in the podcast, I invite you to go out to the podcast's website, www.thescientificodyssey, all one word, .typepad.com. I have more information out there about the scientists, links to various things, places for you to go and find more information. Also, if you like what you're hearing, please recommend the podcast to other folks. I'd love to have this spread to as many people as possible. Finally, take a few minutes to leave us a review at whatever service you're using to download and listen to the podcast from. Those ratings and reviews help keep the podcast on the front pages of those services, and that way we can get the word out to more folks. So, thanks for your time, thanks for listening, and until next time, full sails on your journey.